Alright, in this video what we're going to talk about are trig derivatives. But before we get started, there are two very important limits that we need to look at. So first, the limit as x approaches 0 of sine x over x is going to equal 1. And the limit as x approaches 0 of cosine of x minus 1 over x is going to equal 0. Alright, also, wouldn't be a bad idea to remember some trig stuff. So we have these additive identities. So sine of alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. Cosine of alpha plus beta equals cosine of alpha times cosine of beta minus sine alpha sine beta. I always like to remember these with a little song. So sine, cosine, cosine, sine, cosine, cosine, sine, sine. Also, don't forget the fundamental trig identities we have here. So remember, sine of theta equals 1 over cosecant, and all the rest. Also, the quotient identities, so that tangent of theta equals sine over cosine, cotangent equals cosine over sine. And I'm going to add one that's probably my favorite and one of the most important ones, which is that sine squared theta plus cosine squared theta equals 1. Alright, so now that we have those, what we are going to start talking about is trig derivatives. So to start off with, let's say that we want to find the derivative of sine of x. So in order to do this, we are going to go back to the definition of a limit. So if we look at the limit of sine of x, and that's going to be our function f, that would equal the limit as h approaches 0, sine of x plus h minus sine of x, all divided by h. So if I just leave this here, there's nothing I could do. So I can't cancel out any h's, I can't combine these signs. So this is where the additive identity comes in. So I can rewrite that sine of x plus h as sine of x times cosine of h minus cosine of x, yep, that's a plus, times sine of h, all minus sine of x, divided by h. Now you see, that doesn't look super awesome yet, but it's about to. So if we look at this formula, what we can see is that this term here and this term here both have a sine of x. So let's put those signs of x's together. So that's going to become the limit as h approaches 0, sine of x times, so if I factor a sine of x out of this term, I'm going to be left with cosine h. If I factor a sine of x out of this term, I'm going to be left with a negative 1 plus cosine of x, sine of h, all divided by h. Now, here's the cool part. If I'm adding two terms and dividing by h, I can split those up into the limit as h approaches 0, sine of x times cosine of h minus 1, all divided by h, plus the limit as h approaches 0 of cosine of x times sine of h, all divided by h. Alright, are you ready? The magic's about to happen. So, if I look at this piece here, well, from that limit that I showed you at the very beginning of the video, if I have cosine of x minus 1 over x as x approaches 0, then that limit will equal 0. So here I have the limit as h approaches 0, cosine of h minus 1 over h. So this whole thing is going to equal 0. Now over here, I have sine of h divided by h, and if we look back at that sweet limit that we got at the beginning of the video, sine of x over x as x approaches 0 equals 1. Therefore, this guy is going to equal 1. And what we are left with is the limit as h approaches 0, sine of x times, well, this whole thing is going to evaluate to 0, plus the limit as h approaches 0, cosine of x times, well, this whole thing is going to equal 1. So what we're going to be left with is cosine of x, which is going to be the derivative of sine. Great, we can derive the rest of the trig derivatives the same way, but instead of doing that, I'm just going to give them to you. So our trig derivatives are the following. Make note that you need to memorize these. So sine of x, if we take the derivative of that, is going to be cosine. The derivative of cosine is going to be negative sine. The derivative of tangent is going to be secant squared. Derivative of cotangent is going to be negative cosecant squared. Derivative of secant is secant tangent, and the derivative of cosecant is negative cosecant cotangent. So let's use these rules to evaluate the following. So here we have cosine squared of x, and we want to take the derivative. Well, we haven't really talked about how to take the derivative when we have a power, but what I can do is I can rewrite this as the derivative of cosine of x times cosine of x. And what I can use now to find this derivative is I can use the product rule. So remember, the product rule is the derivative of the first, which would be negative sine x, times the derivative of this, or times the second left alone, plus the first one left alone times the derivative of the second, which would be negative sine of x. And what I end up with is negative 2 sine cosine as my solution. Alright, go ahead and pause the video and try this one on your own using the quotient rule. Alright, so we're going to use the quotient rule on this one, which remember is going to be the bottom, that's going to be sine x plus 1, times the derivative of the top, which is negative sine x, minus the top times the derivative of the bottom. So the derivative of sine is going to be cosine, and the derivative of 1, well, that's just 0. So we'll just be multiplying that by cosine, divided by the bottom squared. Great, let's see if we can clean this up a little bit. So this is going to be sine, negative sine, squared x, minus sine x, minus cosine squared x, all divided by sine x plus 1 squared. Now let's see, is there any way that I can simplify this out? Well, I have a negative sine squared theta here, and I have a negative cosine squared x here. So what I can do is I can put those together. So negative sine x, I'll put that guy in front, minus, now if I factor out a negative out of here and here, I can rewrite these as sine squared x plus cosine squared x divided by sine of x plus 1 squared. Now here's the cool thing, is that sine squared x plus cosine squared x, well, that just equals 1. So I can rewrite this as negative sine x minus, well, this whole thing became 1, divided by sine x plus 1 squared. Now notice that this is a negative sign and this is a negative 1. So I can pull a negative out of these. Negative sine x plus 1 divided by sine x plus 1 squared. Well, this guy will cancel with one of these. And my final solution will be, so let's see, that's going to be negative 1 on the top, so I still have that negative, divided by sine of x plus 1. I can't simplify that anymore, so that will be my solution. let's keep going. Let's look at evaluating this derivative here. So I'm going to have to use the product rule. So I'm going to let this be my f, and I'm going to let this be my g. So remember, we have to figure out what f prime is. So that's going to be 1 times cosine of x plus x times negative sine of x. G prime is going to be cosine of x. So when I'm finding the derivative of f times g, that is going to be the derivative of f, which is cosine x. That's going to be negative, so minus x sine x times g left alone plus, then we're going to leave f alone, so that's going to be x cosine of x times the derivative of g, which is cosine. Alright, let's see if we can clean this up a little bit. So that would be cosine of x minus x times sine of x squared plus, and this would be x cosine squared x. Alright, notice that I can't factor an x out and have sine squared plus cosine squared equal 1 because I have this negative here. So this is as far as I can go. Leave it like this. Alright, the next one is that we actually want to verify something. So let's try to verify that the derivative of cotangent is in fact negative cosecant squared x. So what we can do is go ahead and let's rewrite cotangent as cosine x over sine x. We want to find the derivative of this guy. So using the quotient rule, that's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Alright, so I can rewrite this as negative sine squared x minus cosine squared x all divided by sine squared x. Now, I can't cancel this sine squared with this sine squared because the only thing that can cancel division is multiplication, and these two terms are subtracting. However, see this negative and this negative? I can pull that out. So that'd be negative times sine squared x plus cosine squared x all divided by sine squared x. And what happens is that this top portion is going to become 1 by the Pythagorean theorem. So it'll be negative 1 over sine squared x. And remember, 1 over sine is cosecant, so I can rewrite this as a negative cosecant squared x. Should be my solution. Great, so now that we have a little bit of practice using the derivatives of cosine and sine and those together with the product and the quotient rule, let's take a look now at how to use those two new fancy limits that we were talking about. So here, let's say that we want to evaluate the limit as x approaches 2 of sine of x minus 2 divided by x squared minus 4. So notice that if I plug 2 in, I'm going to get 0 on the top and 0 on the bottom, which is bad news. So what we're going to do instead is, let's see if we can change the way this looks a little bit. So we're going to have the limit as x approaches 2, sine of x minus 2 divided by, well, this is a square, which is x squared, and this is 2 squared. So that means I have the difference of squares. So I can rewrite this as x minus 2 times x plus 2. Now here's a fancy thing I'm going to do. I'm going to let theta equal x minus 2, which means that theta plus 2 would equal x. I'm just going to do some substitution. So, as x approaches 2, what would my theta be approaching? Well, that means theta would be going towards 0, and I can rewrite this as sine of theta divided by, well, x minus 2, that's theta, times, well, I have x plus 2, well, I can replace x with theta plus 2. So that would be theta plus 2, which would give me the limit as theta approaches 0, sine of theta over theta times theta plus 4. Now remember, from that limit that we talked about earlier, this guy is going to equal 1. So I will be left with the limit as theta approaches 0 of 1 times, and remember this theta plus 4 is on the bottom, so we could rewrite it like this. So let's see, as theta approaches 0 now, I'm going to have 1 times 1 over 0 plus 4, which would just leave me with 1/4. Alright, go ahead and pause the video and try this one out on your own. Okay, so to start this one, again, if I plug in 0, I'm going to have 1 minus 1, which is 0, divided by 0, which is no good. However, notice that this is a perfect square, and 1, well, that's 1 squared, so that's also a perfect square. So I can rewrite this as the limit of theta approaches 0 cosine of theta minus 1 times cosine of theta plus 1 divided by theta. Now that's really neat because cosine theta minus 1 divided by theta, as theta goes to 0, this is going to equal 0 by that nifty little limit that we had at the beginning. So what this is going to become is the limit as theta approaches 0, well, that guy's just going to be 0, times cosine of theta plus 1. So if I plug 0 into this, I'm going to have 0 times, well, cosine of 0 is 1. 1 plus 1 will give me 2. So my limit will be 0. Alright, let's look at one more. So we have the limit as theta approaches 0 of sine of 2 theta over theta. Now, well, I can't just use the limit that I had before because that was if the inside and the bottom were the same. So here's what I'm going to do. I'm going to take this, I'm going to multiply it by 2 over 2, which is just a fancy one. When I do that, what happens is that I get the limit as theta approaches 0. I'm going to take this 2 and go ahead and put it out in front, times sine of 2 theta divided by, well, 2 times theta, that would be 2 theta. Now what I can do is I can rewrite this and say, let x equal 2 theta. Well, that means as theta approaches 0, x will also approach 0. So this will be the limit as x approaches 0 of 2 times sine of x over x. Well, I know that this is going to go to 1, so the limit then would be 2 times 1, which would give me 2. Not too bad. If we look at this one, go ahead, try it on your own, pause the video. Alright, so what we want is that we want the bottom to look the same as the top. So what I'm going to do is I'm going to multiply this by 3 over 3. So when I do that, I'm going to have the limit as theta approaches 0 of 3 times sine of 3 theta divided by, well, 5 times theta times 3 is going to give me 5 times 3 times theta. Now, because multiplication is commutative, that means that I can move these numbers around and the order doesn't matter. I'm going to have the limit as theta approaches 0 of 3. I'm going to go ahead and take this 5 and pull it out in front. So 3/5 times sine of 3 theta divided by 3 theta. And if I do the same thing I did before, so let x equal 3 theta, then we're going to have the limit as x approaches 0, because as theta approaches 0, my x would also approach 0. 3/5 times sine of x divided by x, well again, that's just going to equal 1, so our solution would be 3/5.